So now that we've created some instances for our rocks, let's take a look at scattering those on the terrain. But before we get into the actual scatter setup, I'd just like to talk a little bit more about packed geometry, because I kind of glossed over that as I showed you how to pack that geom and load it as a packed disk instance and etc. Now, if we were to take raw geometry of one of these rocks, these are pretty high-res rocks that I made. It's like around 10,000 polygons for this one. And if we'd make lots of copies of it, that's obviously going to get very heavy very fast. Case in point, if we just create a grid, 100 units across, and let's scatter perhaps, 100 points on here, like so. And we can use our copy to points SOP to, assign the rock instances to all of these points. So let's take one of these rocks before it's been packed up, and that'll go into the first input, the geometry to copy, points that we're instancing that onto in the second input, and here we have this one rock instanced all over the place. And this is 1,000,000 polygons when we have this many copies of that kind of high-res rock. My RAM usage is 35%, and if we start to crank this up, then this can start to get pretty heavy for my machine to handle. So if I increase that 10 times, I guess the RAM hit's not too bad. I have a 64 gig RAM machine here, and if I turn this up by another factor of 10, you can see it's taking a little while for this to compute. Sometimes when things take a while, I will generally edit that out so you don't have to sit here waiting for it to cook. So sometimes if you see things happen really fast on my computer, they might actually be taking a bit of time that I've just edited out. And in this case, our RAM usage is going through the roof. I've just tried to do 10,000 copies of that rock, and we might crash Houdini here. I'm at 93% of my RAM, and I'm not sure if we're going to save this session. Now, making that many copies of our rock geometry did in fact crash my Houdini session, and one way that we can kind of avoid that problem is on the copy to point SOP, we can turn on this pack and instance option. So this will create packed copies of the geometry on all of the points, and you can see it's displaying 1,000 fine. If we turn that up 10,000, it's instant. Even 100,000, it's just about instant to display that. And because this is turning into a lot of geometry to display, you are running into those viewport optimization issues. But I shouldn't call them issues because our computers have limits, right? But in the display options, I showed this to you in the last video, on the Optimize tab, there are these controls where you can adjust the threshold for how much optimization it's doing. And you can turn it off entirely if you want. I'm just going to leave this on its default settings though, because we're not going to get nearly this crazy with the rock instancing that we're going to do on the riverbed. Let's turn this back down to something more reasonable. Now all of these packed geometries are all referring back to the same rock mesh. So we just essentially have containers for each one of these instances, and each one of these, just has a reference to that other data. And there are a few ways of storing this data for these instances. In this case, where we're just kind of packing this geometry live in Houdini, whether we use this pack and instance option, or if we turn this off and then connect this packed geometry for the rock here, let's instance that instead. You can see this works just fine as well. It's essentially the same thing. And these packed objects are being stored in memory. And the packed disk instances work a little bit differently. If we connect this cache here, which seems to be an invalid frame, so let's go to a different frame where we have cached out a rock. There we go. If we look at the spreadsheet for these packed objects, there's a lot of data being stored here that you don't see right away. Now the path for packed disk objects will give us the actual path to this on disk, and there's also a lot of data stored that are intrinsic attributes that are kind of hidden away because you don't really need to mess with them directly most of the time. And if you go to this intrinsics dropdown, you can show all of them if you want. And some of them are grayed out because we can't really change them. For example, each instance has some information about its bounding box, and that's not something we can change. It also has an intrinsic attribute that's pointing to the data on disk that it's reading here. And this is why packed disk instancing is really good for rendering, because we don't really need to do an entire scene translation on all of the raw geometry if we tell the renderer to just grab these instances of geometry directly from disk. Now, all renderers tend to handle instancing a little bit differently. Redshift works nicely to just reference these files directly at render time, and we'll take a look at that a little bit later. But ultimately, this is how those packed disk instances are working via those references to the data on disk there. And because we need to have position data for where each of these packed objects is located, we need to have a transform matrix for each one of these. And there are a few types of matrices. We don't need to get super deep into this right now, but there's a packed full transform, packed local transform, and we have a regular transform intrinsic attribute as well. And you can see some of these can't be modified. A lot of these are already grayed out. Like these packed full transforms, yeah, we can't really mess with that directly. But if you need to, there is a packed transform that you can modify. And these intrinsic attributes for packed objects can be a little bit confusing to work with, so I don't really want to get too heavily into it right now. I just want to give you an understanding for how Houdini is, positioning all of these instances behind the scenes. So we've established that, these packed disk instances just use this file name intrinsic attribute to reference these objects from disk. But if you remember, I mentioned that the packsop, or the copy to points with its pack and instance option, these will create in-memory packed objects. It's just stored in RAM, it's not reading it from disk or anything, so some of the intrinsic attributes you see will be a little bit different. Here there's no file name intrinsic attribute because it's not being read from disk, so if you see a difference in the intrinsics, that's one potential reason why. Now I should also point out that the packsop right before the file cache is kind of redundant because this file cache is loading up these rocks as packed disk primitives, regardless of how they're cached out on disk. So if we set this to just a regular geometry load, this is loading up some in-memory packed geometries because that's how we've cached this out. But we can absolutely just bypass this packsop and we can recache this to disk. And then if you middle mouse on that, you can see this is now loading in regular polygons. And if we go back to our load from file, tell this to load packed disk primitives, this is once again going to load up instances for all of these rocks, without actually packing them before writing them to disk. Now I mentioned that we use transform matrices to define the positioning of all of these rocks, and that's only partially accurate. I used a point jitter to kind of move these packed disk objects apart so that we could see them more easily. That's because, the point jitter just modifies the P attribute. And this P attribute is what is actually used to define the world space position of the instances without caring about the rotation or the scale. So if we take a look at this grid example here, maybe let's put a mountain sop on the grid like so. Let's give this a big element size, 30 and 30. Okay. Now let's once again hook up our copy to points to our packed disk instances and display that. And you can see that, as we're changing the position of all of these instances here, if we look at the spreadsheet then you'll see that this P attribute is changing. So I'll pull that down, I'll just bypass the mountain stop. And yeah, the P attribute on each instance will define the position in space, and you'll see that the intrinsic transforms are still 0. Or I should say it's 0 for the rotation and 1 for the scale, which is why you see 1s and 0s in this transform intrinsic attribute here. Now, as soon as we start applying rotations and scales to these objects, then you'll see the transform attributes start to change. So let's turn down the number of instances, and this copy to point SOP knows to look for specific names of attributes on the scatter points to define how this instancing is done. And if you look at the help doc for the copy to points, then you can find some information about what attributes will be used to control the positioning of these instances. If you scroll down a bit, you can look at the instancing point attributes here, and this is definitely worth a read through. All of these things could be very useful for controlling your instancing, and we'll just focus on a few of those key attributes here. One of the most important ones is going to be p-scale, which is a uniform scale on the object. So let's use an attribute randomize, and we'll call this p-scale. Drop this after the scatter, and let's set the min and max to go from a size of 3 to a size of 15. I'll rename this to be p-scale. And then if you look at the copy to points, it's varying that size based on that attribute. And this is, a nice way of controlling the p-scale, but for scale in particular, I like using some different options on this randomize. Usually for p-scale, I'll use a custom ramp option here, because almost any time you're doing instancing type effects, especially for something like destruction debris or something like that, you often want to have lots of little pieces and only a handful of middle-sized to larger pieces. So with the custom ramp option on this attribute randomize, we can control the distribution of these sizes. So if we pull the ramp down kind of like that, and then set the maximum and minimum values, let's try something like value of 2 for the little ones, and up to a value of, 30 for the big ones. Maybe that's excessive. Let's do 2 to 10. Okay, this will help us to exactly control the distribution of sizes just how we want. This is a very powerful way to control your instancing. So now if we look at the transform, you can see that a few of the columns of our transform matrix here are changing. And these columns were a value of 1 before, because a scale of 1 means no change essentially. And now these are getting the randomized scaling applied to our transform matrix there. These 0 columns are going to be for rotation, and we have a few different ways of driving the rotation of our instances. And one of the easiest and most commonly used ways is to just use a random normal attribute on the points. So let's do another attribute randomize. That's defaulting to color, which the copy to points is also picking that up automatically. But let's change this to be n instead. And you can use this uniform method for random normals if you want, and change that to -1 to 1. And you can normalize that. And this will work to apply random rotation to all of these pieces. But there are a couple other options you might want to use as well. Inside sphere is, kind of helpful, but it's not necessarily going to be in a specific normal length. So you might want to use direction or orientation. It doesn't really matter too much which of those methods you use, as long as you get some nice randomness in there. And if we look back at our geometry spreadsheet, now you can see we're getting all of these rotations stored in that transform matrix. Now this is all well and good, but currently we're just grabbing one rock instance and applying that to everything. If we disable our p-scale and our normal attributes, and I guess we can disable the mountain as well for clarity. These are all the same exact rock being applied to all of these points. And there are a few different ways that you can vary up the instances that are assigned here. And a more old school way of doing this would be to use the copy stamp SOP. For a while, this was one of the best techniques for getting variations across all of the different instance points. And there are still some cases where you might want to use a copy stamp SOP if you really need to do a lot of modification on what's being instanced to the points. Sometimes this can be good, but generally speaking, that's much less efficient than using this copy to points. And copy to points has this piece attribute option that can be used to control which instance is assigned to which point. So if you turn that on here, you can see it's going to complain right away because this default attribute that it's using, variant, is not existing on either the points or the instances themselves. So we can apply that attribute in a number of different ways, but I like using this enumerate SOP. Just drop this before this instances high-res null, and this will just create a new attribute that essentially just stores the point number or the primitive number for each point or prim. So on this enumerate SOP, let's just set the attribute name to variant to match what copy to points is expecting. And if we attach this as the geometry to instance now, you'll see that we're not getting any specific variants yet. We're getting every single rock instance applied to every single point, because we need to have the variant assigned to all of these points as well. And to get this randomized variant attribute on the points, we'll just use another attribute randomize, drop that on here, attribute name is variant, rename that for clarity, and we're going to use, instead of continuous values, we're going to use discrete values. Now, if we set a value from 0 to 20 on this randomize for the variant and look at the spreadsheet, you can see this is giving us, it's actually a vector variant because we have 3 dimensions set on this randomize, and these are float values, with a fair amount of precision. And if we compare that with the variant attribute on our instances here, this enumerate SOP, I'll rename to variant instances. Then if we check the spreadsheet there, you can see that these primitives have a variant attribute going from 0 to 19. And the variant attribute has to match perfectly between the points and the instances. So we don't want to use these float values for the variant. We want to switch this from uniform continuous to uniform discrete. And this gets us part of the way there, but these are still decimal values, and they won't match up correctly with the integer values that we saw on the instances. Also, we have a vector here because this is 3 dimensions. Let's turn that down to 1 so that we only get a single value there. And actually, we forgot to do that on the p-scale also. And the p-scale worked okay when we created a vector for p-scale. I'm guessing it only looked at the x component of that, the first component there, but p-scale should really be 1 dimension as well. But I'm going to leave p-scale disabled for the moment. And on this variant, I generally like to link this value range to the number of instances we're working with. So on this randomize for the variant, I'm going to put a function in the max value. We're doing an endpoints lookup to get the number of points on the instances high-res null. So point that endpoints expression to // instances high-res. And because this has 20 packed disk objects, that's represented by 20 prims and 20 points. So this will return a value of 20, but because our numbering starts at 0, we need to subtract 1 from this to get values from 0 through 19. Now if we go back to our attribute spreadsheet for our scatter points and we sort by the variant attribute, you can see these random values go from 0 to 19 just like we want. Now if we look at this copy to point SOP, it's still not working. So if you middle mouse on here, you'll see that it's complaining that the target piece attribute is a floating point attribute and it has to be an integer or a string. So one way to fix this is using the attribute cast SOP. And this is not a SOP that you probably need to use very often, but it can be really helpful for debugging some tech issues like this. And this will allow us to change the type of this variant attribute from a float into an integer. I'll just pick the 16-bit integer here, and we'll have to put in the attribute name, which is variant, and there we go. Now we're getting unique instances applied across all of these points. Bring back the p-scale and bring back the rotations, and there we go. We have some nice randomness. Now I'm just going to go through my setup for the riverbed area instancing kind of quickly because we've already looked at all of these concepts. And you'll notice there are some display issues happening in here. Sometimes the Houdini viewport just kind of glitches out a bit when displaying some packed geometry. Some of these problems can be fixed just by going to the render view and back to the scene view, and that can refresh these problems in some cases. Now in this example, I've set up two different sets of rocks that we can control independently. So we have these kind of pointy rocks that are sticking up in the middle of the river area, and then we have some other rocks kind of piled up along the sides. And this is something where you might want independent control over those two different types of rock placements. So to go through the central ones first, we're just bringing in the terrain and defining that central area by using a blast SOP and deleting everything with a mask value less than 1. And then we're doing a scatter. And on this scatter, I've turned off the relax iterations. This is on by default, and this tends to kind of spread out and evenly space the points. But sometimes this is a bit less natural, and it can be a little bit more natural and organic to turn down the relax iterations or turn it off entirely. You get a little bit more clumping of points, and it's a little bit more randomized that way. And then I'm just doing the p-scale with a custom ramp like we've seen before. And I'm doing a non-uniform scale to stretch these rocks out in the y direction. So you can see they're a little bit taller here than the original instance shapes were. And then I'm doing something slightly different on the normal attribute. So if we display point normals, you can see that all of the normals are pointing upwards with a little bit of variation. And I wanted to make sure that all of these elongated rocks were kind of, pointing upwards like that. So I didn't want to give it a totally random normal in any direction. So on this attribute randomize, for that n attribute, I've turned on this cone angle option, which is off by default. Turn that on, set it to an angle of 30 with a direction upwards and y of 0, 1, 0. And from there, it's just the same variant workflow that we saw before. Same copy to points SOP, nothing different here. And I found that after I did this initial scatter, it was a little bit too dense and it didn't really give us enough room for this river sim to flow nicely. You might find yourself needing to revisit this rock scatter once you start doing the river simulation because you might not like how it's responding to how you initially set up this rock instancing. So sometimes it makes sense just to do a little bit of cleanup after your procedural scatter. So I've just, selected a bunch of primitives to delete just based on their prim number, selecting them interactively in the viewport, and blasting them away until I got something that looks a little bit nicer like this. And now for the rocks on the sides, it's pretty much the same thing. I've used a blast sop just to define the areas along the sides of the river. We're deleting anything with a mask value less than 0.6 or a mask value equal to 1. So that gets rid of the stuff outside of the river area and gets rid of the central area. And because that created some unconnected points here, I just threw in a clean sop to get rid of those unused points. And then I did a slightly different thing here where I've used a ray sop to calculate the distance from the sides of our scene here. Now this ray sop is often used to push geometry onto another surface. This ray sop, is taking this extra, sides of the environment as an input, and the method is set to minimum distance, which by default, would push all of the points to the closest point on the side of the scene. So if I re-enable transform points, you can see this is all getting stretched out to be pushed onto that geometry. And that's what ray sop will do by default. But I just turned off the transform points and turned on the point intersection distance, which will create this dist point attribute. And this is a really helpful and easy way to just calculate distances between points and objects, which can be useful for many different things. But in this case, I just deleted the points that were within a distance of 3.1 from the edge of the object. The reason I did that was because I felt like it didn't look very nice when the rocks kind of hang over the edges of this environment. I really wanted this circular cut of the environment to be pretty cleanly clipped off there. Didn't really want those rocks to spill over the edge, which is why I'm doing this distance calculation with that extra little bit of trimming there before we do the scatter along the sides. And that's really the only thing that's different about the sides scatter here. P-scale, same deal, some different values, but similar custom ramp control there. For the normal direction, I left this fully random because I wasn't really trying to do those stretched out rocks like I was in the center. I've disabled the nonlinear scale, or I should say the non-uniform scale. And then once again, the variant setup is the same as before. And that gives us this nice set of rocks along the side of the riverbed there. And if you want to leave the general setup the same, but just get some different variations of this specific scatter result, you can always, play around with the seeds on your randomizers. Like we can go to our scatter and we can play around with this seed here to get a placement that we like. And same thing with any of these other randomizations. If you just want to, generate some different variations here. And once you find a rock scatter that you like the look of, it's a good idea to cache out these scatter points. Because if you go back and you make any tweaks to this terrain mesh, you might not want that to change all of the rock scattering that you've already set up. Even the slightest change to this terrain mesh can completely change the rock scatter results. So you can just drop in a file cache, set that to save out a single frame, and ensure that you always have this nicely designed rock scatter set up the way you want it, that's protected from any upstream changes that you might make later. And of course do the same thing on the sides as well. And don't forget to load from disk or else these caches will not do anything. You'll also notice that I have a few additional hand-placed rocks that aren't part of my procedural scattering setup. With my particular version of the terrain, this really kind of flattened out quite a bit here, down at the end of the river here, and I wanted to make sure that we had a nicely defined side of this river wall that would kind of guide that water out without it kind of spilling weirdly into this flatter region. So there's nothing wrong with doing some hand placement as well to design things just how you want them. So here I've just gone in and I've just grabbed a specific instance that I like the shape of. I've grabbed a couple different ones here and just, manually transformed those into place with a transform sop. And then just merge those in with the rest of the rock instances. And even though these manually placed rocks aren't using this copy to points to, do the instancing onto points, these are still, reaping the same benefits of being packed disk objects. You don't have to, use copy to points to benefit from packed disk instancing. As long as we're loading in these packed disk objects, whatever we do with them, as long as we don't unpack them, we'll be benefiting from this extra efficiency. And as I said, these rocks are really high res, so certainly feel free to make your rocks lower resolution, or you can do something where you swap in, different resolution rocks for the wide versus close shots. It's kind of up to you, but yeah, my computer handled this fine, so I didn't worry about it too much. And yeah, now we've got this nice environment, and we can move on to design the creatures and the animation and rendering and effects and all of that glorious stuff.